Hi folks, we're going to take a look at our first calculus assignment on limits and continuity. I hope that the resolution's okay. If something doesn't make sense, feel free to pause, go back to it. Here we go. We're going to use the graph to find some limits. Taking a look at number 1, we're going to find the limit as x goes to 1 on this. So as x goes to 1, from both sides, we seem to be approaching a value of -1. So that'll be the answer here. The limit is just the y value that we're tending towards, or the y value that we seem to be going towards. The next one is 0 from the left. So 0 from the left seems to be going to a y value of 0. 0 from the right also seems to be going towards a y value of 0. D says the limit as x goes to 0. Well, it's going to the same place from the right and from the left. It's going towards 0. Now, E asks us, what's the actual value of the function at 0? The value of the function is way up here. It's at 2. So the limit is what the graph tends towards, or seems like it's going towards, and the actual value is what it really is. The limit as x goes to -1. Let's see. As I go to -1 from the right, it seems to be going to +1. As I go to -1 on my x from the left, it goes to 0. It's not going to the same value from both sides, so this would be no limit, or does not exist. G is the limit as the function goes to 2 from the right. So 2 from the right is going up towards infinity. H is as x goes to infinity. Well, as x goes to infinity, notice we have a horizontal asymptote. It's going to get closer and closer to 1. And finally, the value of f at 1, the y value is -1. We're asked to write down the equation of the vertical asymptote. So the vertical asymptote, vertical line, takes the form x equals a constant, and this will be x equals 2. Next, we're looking for where the discontinuities are. And our intuitive definition of discontinuity, or points of discontinuity, is where you have to lift your pen. So I'm going along the graph like this. I have to lift my pen at x equals -1. Keep going along the graph. I'd have to lift it at x equals 0. Keep going along. I'd have to lift it at x equals 2, and then never again. We're going to classify each of those discontinuities. So the first one over here, as I went to the left, I had to jump at -1. When I kept going, right here, a lot of people seem to be confused by what type this is. This is a removable discontinuity. If you filled in this dot, now it would be continuous. That's what removable means. So it's not that we've jumped up to a value at 0. It's just that we've got a hole. It happens to be filled at 2, but we could fix it by filling that hole. That's what's meant by removable discontinuity. You can fix that discontinuity by filling in the hole. Okay, and the last one at x equals 2 is obviously an asymptote, and we call that an infinite discontinuity. Find each limit if it exists. If it doesn't exist, write does not exist, and briefly explain why not. Okay, so the first one, we've got lim as x goes to 1 of x cubed minus 3 by 2x over 2x squared minus x plus 1. If at all possible, we want to just substitute in our numbers. And in this case, we can. It's not going to cause anything illegal. No division by 0. So we'd have 1 cubed minus 3 all over 2 by 1 squared minus 1 plus 1. Work that out. We get -2 over 2, or just -1. The next one, obviously we can't substitute in here. If I put -3 into root x minus 2, we're not going to be able to deal with it. We can't take the square root of a negative. You know that function looks like this. It's a basic square root graph moved to the right 2. We're asking about its limit over here. It doesn't exist in the neighborhood of x equals -3. So does not exist. We could say the graph doesn't exist in the neighborhood of x equals -3. All right, we'll keep going. This one has nested fractions in it, and I know you probably can't see it on the screen, but hopefully you can see it on your paper. I'll just rewrite it out. So it's lim as x goes to 0 of 1 over 3 plus x minus 1 over 3 all over x. I can't put 0 in. That's going to cause trouble for us because we'd have to divide by 0. So what we can do is we can deal with those nested fractions and try and find a way around dividing by 0. The way we've dealt with nested fractions is we find the LCD of the little ones, which is 3 and 3 plus x, and I times top and bottom by 3 plus x. Okay. As I multiply through, the 3 plus x's are going to divide out on that first term, so I'll have lim as x goes to 0 of, this will just be a 3 for my first term. And then for my next one, I'll go -1/3 times this whole thing, the 3 and the 3 plus x. So the 3's will divide out. I'll be left with -3 minus x all over x by 3 plus x. It doesn't help us much to multiply out that denominator. Keep going. We have lim as x goes to 0 of -x over x by 3 plus x. This is where the magic happens. You can divide out x by x, and you'll be left with just -1 on top. So in our next step, it will look like this. Lim as x goes to 0 of -1 over 3 by 3 plus x. Now, can we put in 0 to that? Absolutely. No problems. So we can say that this is equivalent to -1 over 3 times 3 plus 0, or 3, or -1/9. Okay. Notice how I kept my limit notation until the very end, until I effectively substituted in 0. Next one, D. You can use a shortcut for this, or you can go with the formal method. So shortcut comes from looking at the top, saying the driver of the top, the most important term, is 5x cubed. The driver of the bottom is 3x cubed. That's going to be equal to the lim as x goes to infinity of 5 over 3, or just 5 over 3. Okay, because as we go to infinity, 5/3 just turns into 5/3. If you wanted to go more formal with it, here's what we'd do. Lim as x goes to infinity of 5x cubed minus x all over 3x cubed plus 2x plus 1. I would multiply the top and bottom by 1 over highest power of the bottom. So 1 over x cubed. And here's what I'm going to get. Lim as x goes to infinity of 5 minus 1 over x squared over 3 plus 2 over x squared plus 1 over x cubed. Okay. As those go to infinity, 1 over x squared is going to become 0. 5 will become 5. 3 will become 3. 2 over x squared goes to 0 plus 0. So that's going to give us 5/3. Either way is fine on this. Okay, last one, E. I guess before we go there, you recognize the opportunity to do this on these questions because you're going to infinity. Okay, as we go to infinity, that's when we care about the driver above all else, the most important term in any expression. So up top, that was 5x cubed. Down below, it was 3x cubed. Okay, the last one. What makes this one fishy is that we've got trig over something x. Okay, and here was the fact that we know. We know lim as x goes to 0 of sine x over x is 1. That's a fact for us. We proved it. We looked at it graphically. It was the long proof that we did in class. Okay, so in this one over here, what I would really like on the bottom is a 6x. If I had sine 6x over 6x, then I'd be able to know that that part at least is 1. Well, I can build a 6x on the bottom. I just times everything by 3. But if I times it by 3 on the bottom, I need to do it on the top as well. So my next step looks like this. 3 by sine of 6x all over 6x. Okay? And notice we couldn't have substituted 0 in here. You can't divide by 0. Okay? That is the same as 3 times sine of 6x over 6x. And we know that when we evaluate the limit, this becomes 1, and this becomes 3. So you have 3 times 1. Notice how I'm actually using the limit now. So I don't have my limit notation anymore. I used it up, and I get 3 in the end. Just want to talk briefly about the common mistake that I saw on this one. I saw a lot of this, and I'm just going to write right here. This is bad. So sine 6x over 2x turned into sine of 3x over x. People just reduced these down. You can't do that. The sine 6x, the 6x is part of an angle, and the 2x is more or less a regular entity on the bottom. You can't divide those out. And if you did, then why didn't you just divide out the x's too and say, oh, it's sine 3? And if that were all true, then sine 30 over 2 would be equal to sine 15. No, these things are all false. Okay? So you can't reduce from this term to this one, the one below. Okay? So the method shown when we went through the question, that's what we want to do. Okay, next one, squeeze theorem or sandwich theorem. We want to find the lim as x goes to 0 of x cos 1 over x squared. Okay? We need a good setup. So we're dealing with cos 1 over x squared, and cos of anything is between 1 and negative 1. Now I need an x out front, so I'm going to multiply each of the 3 parts of this inequality by x. Obviously, I can't substitute in 0 because that would be cosine of undefined. But I can evaluate the limits that are on the side. So as x goes to 0, negative x becomes 0. As x goes to 0, x becomes 0. Therefore, this thing is sandwiched in between 0 and 0. It must be 0 as well. Okay. And that's the kind of justification we want to see. End behavior model, that's a lot like limit as x goes to infinity, but we're talking about what basic function it looks like. So this is a complicated function. that you see in 4, but it can be modeled by something that is a lot simpler. All we do is take the highest power on top, highest power term, divide it by the highest power term on the bottom. And that gives us y equals 3x over 5. Or a line with a slope of 3/5. So that complicated function in 4, in terms of its long-term behavior to the right and left, looks like this easy one, this basic line. If you were interested in what happens to the function around a million, it would be a whole lot easier to substitute into its end behavior model. Okay, end behavior model for e to the x minus x. So left end means x is going to negative infinity. If I put negative infinity, or negative a huge number in for e to the x, e to the negative infinity, or negative a bajillion, is going to be 0. This one is going to turn into positive infinity, or something that's really big. So what's making more of a difference on the left end? The e to the x, which goes to 0, or the x, which is big? Obviously, it's the x part, or the negative x part of the function. Let's do the same thing for the right end behavior. That means as x goes to infinity, as x goes to infinity, e to the, say, e to the million is huge. Minus, let's say we put in a million, just a big number. Well, a million is big, but it's not huge. It's not as big as e to the power of a million. E to the power of a million will probably break your calculator. Your calculator won't be able to give you a good approximation. Okay, so what's making a bigger difference here? It's the e to the x. And again, what that tells us is, if you looked at this graph, which is kind of tricky, on the right end, it kind of has this look. On the left end, far left end, it has this look. Okay, number 6, we're going to graph the piecewise function. This first part here, y equals x, that's a line with a positive slope, and that's wherever x is less than negative 1. Okay, so I'm going to sub in and figure out what's going on at negative 1. If I put negative 1 in for x, I'll get negative 1 for y. It's not included, so it gets an open dot, and it's a positive slope. There's the first piece of the piecewise. X cubed. We know that looks like this. It's going to have endpoints at negative 1. And notice how that's included. So now we can fill in this dot. And 1, which is not included. So I'm going to need an open dot. Okay. Lastly, we want to look at what happens when x is greater than 1. So that's a line with a negative slope. If I put in 1 for that, I'll get negative 1 and negative slope. So there's the basic look. I'll show you some of the things that I saw that were issues. People would take this function and then extend it over here. It only has that rule where x is less than negative 1. Let's undo that. Okay, another common thing that I saw was extending the cubic function so that it looked like this. Again, it only follows that rule for this piece. Okay, now that we have the graph, let's find those limits. As x goes to negative 1, well, let's just follow it. X goes to negative 1 from the left, and from the right, oh, it looks like it goes to a y value of negative 1. Great. As x goes to 0, we're going to a y value of 0. As x goes to 1, looks like I'm going to 1. Except if I come at it from the right, I'm going to negative 1. Oh, geez, they don't go to the same value. Therefore, there's no limit. Or you can say dne. The kind of discontinuity we see as we go through the graph is a jump discontinuity. And when I say classify, I mean tell me what kind of discontinuity. Equation of the horizontal and vertical asymptote. So same power on top and bottom here. So the horizontal asymptote is going to be 2x over x, or y equals 2. I don't want you to say horizontal asymptote equals 2. The equation has to have an x or a y in it. And from the equation, that's an x minus 3 on the bottom. Therefore, there is a vertical asymptote at x equals 3. And that stuff is from chapter 9 from the last course. Consider this function. Okay, so I'll write the function out over here. F of x is x cubed minus 3x plus 2 all over x minus 2. Okay, when you see that, you probably want to factor it out to figure out whether we're talking about a vertical asymptote or possibly just a point of discontinuity. Okay. So let's follow this through. This is going to factor into x minus 2 and x minus 1. Oh! So there is a point of discontinuity on this. And it's going to be at 2. We can divide that out if we want. And we end up with this. X minus 1, as long as x is not 2, because this function's undefined at 2. That point of discontinuity comes from subbing in your 2 into this simplified function. And it tells you that you'll have a y value of 1 right there. Now that we know some stuff about this function, now we can talk about the types of discontinuity, how we can fix the function, that's air quotes fix, turn it into a continuous function everywhere. Okay, so discontinuity at x equals 2, it was a point of discontinuity which we call removable. Points of discontinuity mean the same thing as removable discontinuities. So right now we know that this function looks like a line with a positive slope, goes through y-intercept of negative 1, and it's got a point of discontinuity at 2, 1. If you were to give a y value of 1 to this curve right here, now it would be continuous. And its equation would be, in simplest terms, just y equals x minus 1 everywhere, and that would be a continuous version of the original. Or if you want to do it as piecewise, it could be its original equation wherever x is not equal to 2, and it would just take the value of 1 where x is 2. Hope this was somewhat helpful. Again, I apologize for the resolution here, but hopefully with your assignment in hand that you can make some sense out of this. Let me know if you have any questions, and good luck with the rest of the course. Bye-bye.